So we've basically got four different ways that we've discussed to construct new topological spaces from old ones. We have subspaces, coproducts, products and quotients. In the last video we talked quite a bit about compactness of subspaces. In this video we'll talk about coproducts and quotients, which won't take very long, and then we'll leave products, which is a bit more substantial, to a separate video. Okay, so firstly, so suppose we've got two disjoint compact spaces. Then I want to claim that Y union Z with the coproduct topology is also compact. Okay, so as always with a direct proof of compactness, we have to start by supposing we're given an open cover. Okay, so that's an open cover of Y union Z. Okay, so what does that mean? So just remembering the definition of the coproduct topology, that just means that UI is VI union WI for some VI open in Y and WI open in Z. Okay, okay, so then it's kind of clear that we just look at the V's. So then they're going to form an open cover of Y. So that means that we can choose some finite number of indices, say I1 up to IN, with Y being VI1 union up to VIN. So here, of course, we're using compactness of Y. On the same argument, we can choose, say, some other finite list of indices, say, which we'll call IN plus 1 up to IN plus M, with Z being contained in the union of the corresponding W's. And now it's clear that Y union Z is contained in the union UI1 we take the first n of these, all the UIs, well then that's containing the V's, the VI1 up to VIN, and so that covers Y. And then if we take the remaining m of them, UIN plus 1 up to UIN plus m, well, the U's can contain the corresponding W's, and the corresponding W's cover Z. So we've covered both Y and Z, and so now we've got a finite subcover, finite number of the sets UI that still covers the Y union Z, and that's what we need. It's a finite subcover, so we've proved that Y union Z is compact. So now we want to deal with quotient spaces, but we'll do something just a little bit more general. Okay, so different. Okay, so let's let X be compact. And let f from x to y be continuous and surjective. Then Y is also compact. I mean, you should think of compact as kind of meaning small in some sense. And so if we've got a surjective map from a small thing to another thing, then the other thing also has to be small. So the proof, well, as usual, we have to start by giving ourselves an open cover. We've got an open cover of Y, and so we need to find a finite subcover. And we have to somehow exploit the fact that X is compact, so we need to somehow produce a cover of X by open sets. And so we need to produce some open subsets of X. And how can we do that? I mean, basically the only thing that we can do is we've got these open sets VI and Y, and we can take their preimages, because F is continuous, so the preimage of an open set's open. So what we do is we put UI is F inverse VI, which is open in X. Okay, so there's a bunch of open subsets, and we want to claim that they cover X. That's not very, so we need to check that next. So we've got some point X and X, then the image of it lies in Y, and VI's cover Y, so we can choose I with f of X lying in VI, and that's to say that X lies in f of X lies in VI. That's the same as saying that X lies in the preimage of VI. Okay. So that means that the open sets UI, they cover all of X. Okay. So the open sets UI cover X, and X is compact. So there is a finite subcover. In other words, we can choose some finite list of indices, I1 up to IN, where X is just the union of that finitely many finite number of sets. Okay, so okay, so now we want to claim that the corresponding sets VI1 up to VIN cover Y. So to prove that, let's suppose we've got some Y and Y. So as F is assumed to be surjective, we can choose X and X. F of X being equal to Y. But then X lies in capital X, which is the union of this finite list here. We can choose T with X lying in UIT. Now X so lies in UIT, and remember UIT, that's by definition the preimage of VIT. So that means that f of X lies in VIT, But if x lies in VIT, then that means that, well, remember, f of x was equal to y, right? We chose x such that f of x equals y. So we're saying that y lies in VIT. Okay, so that worked for any y and y. We could choose, we found some one of these sets VIT that contains it. So we now have see that y is covered by these finitely many sets here. So we have the required finite subcover. Okay, so we've proved that if you've got if x is compact and we've got a surjective continuous function from x to some other space y, then that space y has to be compact as well. Okay, so now we can return to the discussion of quotient maps. So let x be compact and let E be an equivalence relation. Then then we can form the quotient space, and remember we had a quotient topology on x mod E. So the claim is that that quotient space is compact. And the proof, well, that's immediate from the previous proposition. Remember, whenever we have a form a quotient like this, we've got the projection map that sends a point to its equivalence class, if you like. So this is continuous and surjective. It's kind of tautologically continuous, as we've remarked previously, because that's kind of really built into the definition of the quotient topology. And also pretty much tautologically surjective, because x mod E is just the set of equivalence classes, which by definition is the image of pi. So by the previous proposition, if you've got a surjective continuous map from x to some other space, then that other space is also compact. Okay, so now we know about compactness of subspaces, of coproducts, and of quotients. We still need to know about the compactness of products, and we'll do that in a separate video.